Game theory. What is game theory? So game theory, I would say, is the use of the terminology of a game, like a chess game, and use it to describe a situation where players make strategic decisions. So it's very general if you frame it this way. We're using terminology of a game to describe situations where people need to make strategic decisions, which is pretty much anything important. The goal is to determine the optimal strategy for each player. What should the players do? Now we need to define what is optimal strategy, and we'll do that in a moment. Before we do that, let's think about what constitutes a game. So once again, it's helpful to think about a chess game. If you and I are playing a chess game, what do we have? So there are 4 components, right? You and me playing a chess game. First, there are you and me. We are the players. So a game would have players. You and me playing a game. What else? Now, there are rules in what we can do in chess game, right? The queen can move diagonally or vertically or in any directions. Pawn can only move forward 1 step at a time until it reaches the end. And you have the knight who moves diagonally, the bishop who moves diagonally, and so on. So you have all these rules in chess game. Similarly, in game theory, we have limits on what the players can do. Those are called actions. Third, there must be reasons why we play the game. In the chess game, well, you try to win, and how do you win? You win by taking the king, right? By taking the king. So there are payoffs. There are payoffs in a game. What are the objectives, and how much does it pay? Finally, given the players, the actions, and the payoffs, the players formulate strategies. In a chess game, when you play, that's what you're doing, right? You're trying to figure out what's the best move given the situation. That's strategy. So a game theory, we're trying to use this terminology on all sorts of situations. For example, in the public good example, we can frame it in the game theoretic terminology. The players are David, John, and Paul. The three of them have to decide what to do. The action possible is to participate in the building of the public good or not. There are 2 possible actions: participate or not participate. The payoffs, the net benefit from having or not having the public good, that's the payoff. And the payoff depends on what they do. And finally, we talk about the strategies. The strategies we mentioned is that they will not participate if the good can be funded by the other 2 players alone. So we have mentioned that strategy. So that's a strategy because that's a plan they have formulated given what they're going to get and what's the possible actions. Now, what is an optimal strategy? The word optimal could mean multiple things, right? It could mean that's the best I can do in any given situation, or it could also mean that's the best I can do in the current given situation, and the 2 are not the same, right? Ideally, I want to be as rich as Li Ka-shing, but that's not going to happen. So what's the best I can do right now? In game theory, the optimal strategy, or sometimes there could be multiple, so there could be optimal strategies, for a player is the one that she has no incentive to deviate from. So this best strategy is the one that I am willing to stick with. So in the public good example, where the public good cannot be funded by the other players alone, a player would participate in funding. They would stick with funding. So participation is an optimal strategy in that case. If we don't participate, the public good will not be provided. Since we do want the public good to be provided, I will stay. That's our optimal strategy. But if the public good can be funded by the other players alone, I don't need to participate. In that case, participation is not optimal. I want to change my mind, right? So optimal strategy in game theory is always about whether you want to change your mind. If you don't want to change your mind, that's optimal. Formally, a pure strategy Nash equilibrium is defined as each player chooses a single action. Given what action the other players have chosen, each player has no incentive to change her action. What would be a simpler term? In simpler English, it would be, given what I do, you don't want to change what you do. And given what you do, I don't want to change what I do. Right? You do what you do, I do what I do. That's Nash equilibrium. The Nash equilibrium is named after John Nash, who won the Nobel Prize for his contribution in this area. And John Nash is also the lead character. It's a lead character is a protagonist in the movie A Beautiful Mind, portrayed by Russell Crowe, right? And he doesn't look anything like Russell Crowe in reality. But if you're interested, you can watch that movie too. It's a fine movie. So we'll be coming back to the Nash equilibrium concept over and over again. In game theory, it's all about Nash equilibrium. How do you represent a game in game theory? A game is typically represented in a table, like what you see here. This is called a normal form game. What it implies. Now, the normal form game implies that what everyone has to make decisions together, and we'll come back to that in a moment. Let's first describe what's happening in the game. Now you'll see that I have player 1 on the left and player 2 at the top. So these are the two players in this game. That's the typical way we represent the situation with two players, one on the left, one on the top. Player 1 has two actions, as you see next to him, next to his name. Action 1 and action 2. These are the two possible actions player 1 can do. Player 2 has two actions too, C and D. So we list them next to them. If you have more actions, you just keep listing them in a table. The numbers inside each cell are the payoffs, and it corresponds to the actions. For example, if player 1 chooses action 1 and player 2 chooses action C, player 1 would get 10, the first number, and player 2 would also get 10, the second number. What if player 1 takes action 1 and player 2 takes action D? Player 1 would get 16, the first number, and player 2 would get 9, the second number. Right? The first number is the payoff of the player on the left. The second number is the payoff of the player on the top. Okay, two players. What if you have more than two players? When you have more than two players, then you would have multiple diagrams. So typically, you won't see that very often. Definitely not in this class. So we always stick with two players because the representation is more complicated when you have more players. Actions, player 1 can take action 1 and 2 next to him. Player 2 can take action C and D, one also below her name. Payoffs, as I mentioned, the number before the comma are payoffs for player 1. The numbers after the commas are payoff for player 2. All right, so that's the setup of a game. How do you find the Nash equilibrium? It's actually, so the concept already mentioned to you. Nash equilibrium is a situation where I do what I do, you do what you do, none of us wants to change our mind. How do you find that on a normal form game? The normal form game assumes that everyone make decision at the same time. The best example would be rock, paper, and scissors. When you play rock, paper, and scissors, you move at the same time. You cannot go first or go second. So that's what a normal form game is. you have to make decision at the same time. So, because you make decision at the same time, you don't know for sure what the other player is going to do in the game, right? So you kind of have, just like rock, paper, and scissors. You don't know what your opponent is going to do. So you have to make a decision. You have to make a decision based on some sort of assumption you have about what the other player is going to do. Okay, so the way to do that is to ask what each player would do, assuming the other player is going to take a particular action. So let's start with player 1. Let's say player 1 is thinking about what to do. He first consider what he would do if player 2 were to pick action C. Right? This is an assumption. Player 1 doesn't know that player 2 is going to take action C at this point. He's just assuming that she's going to do that, right? So suppose player 2 takes action C. What would be the optimal response by player 1? Now, if player 1 chooses action 1, he gets 10. If he chooses action 2, he gets 9. Now 10 is higher than 9, and these are payoffs. The higher, the better. So player 1 is going to choose action 1 in this case. So let's highlight that with a square, right? Or a circle. Okay. So let's highlight that with a square. This is what player 1 would want to do if player 2 is going to choose action C. But we don't know that. So we have to consider the second possibility, is that player 2 might want to choose action D. So suppose player 2 chooses action D. What would be the best response of player 1? So once again, player 1 looks at the two possibilities. If he chooses action 1, he's going to get 16 as payoff. But if he chooses action 2, he's only going to get 12. Since 16 is bigger than 12, that's what he's going to choose. All right, let's highlight that with a box. Now we have determined what player 1 wants to do in each possible scenario. If player 2 chooses action C, player 1 wants to choose action 1. If player 2 chooses action D, player 1 also wants to choose action 1. So in this case, he actually wants to choose the same action in both cases. Okay, that's fine. That's his strategy. Choose action 1 in all cases. Okay, that's the strategy. Right? No matter what happens, I'm going to choose action 1. I'm going to choose action 1. Let's think about what player 2 would like to do. So the exercise is symmetric. The two players we just have names we give them, so we can symmetrically ask the same question. So suppose we know that player 1 is going to take action 1, which we actually know right now, but so we have to consider all cases. So suppose we know that, what would player 2 do? Now player 2 have two choices. She can choose between action C and action D. Action C would pay 10, action D would pay 9. Since 10 is bigger than 9, she would choose action C. Right? That gives her a higher payoff. What if player 1 chooses action 2? We know that it's not going to happen, but what if he actually chooses action 2? Well, once again, player 2 considers her payoff. Action C is going to pay 9. Action D is going to pay 12. Since 12 is higher than 9, player 2 would actually prefer action D in this case. So this is a situation where the strategy chooses a different action depending on what the other player would do. Right. So the strategy would be choose C if player 1 chooses action 1, and D if player 1 chooses action 2. Now that we have figured out what the players would like to do, given what the other player is doing, we ask which situation is stable. Remember, Nash Equilibrium is about stability, right? What I do, you do what you do, neither of us wants to change. That means that you would be looking for a situation where all the players are playing their optimal action in that scenario. Let's think about what that means. Now, let's start with the bottom right case. Suppose player 1 is currently choosing action 2 and player 2 choosing action D. Is that stable? Well, player 2 wants to stay with action D, right? Because that gives her 12 instead of 9. Okay, player 2 wants to stay. But what about player 1? Player 1, in this situation, he actually wants to switch to action 1 because action 1 gives him 16 instead of 12. So this is not stable because player 1 has an incentive to switch his action. That's not stable. So now we are in here, in the top right corner. So player 1 is choosing action 1, player 2 is choosing action D. Is this stable? Player 1 is happy. He always chooses action 1, as we have already figured out. What about player 2? Well, player 2 would prefer choosing action C in this case, because action C gives her a payoff of 10 instead of 9. So she is going to change her mind. So once again, the top right corner is not stable. What about the top left corner? The top left corner, player 1 chooses action 1 and player 2 chooses action C. So player 1, well, he is going to stick with action 1 because if he switches to action 2, he's going to get less, 10 versus 9. So he's going to stay. What about player 2? Player 2 is also going to stay because if he switches back to action D, he's going to get 9 instead of 10. So he's going to stay. So this situation is stable. Given what player 1 is doing, player 2 wants to pick action C. Given that player 2 is picking action C, player 1 wants to choose action 1. So this is stable. And stable situation would be a pure strategy Nash equilibrium. Notice that this particular situation, this cell representing the situation, has boxes around all the numbers. right? Because the boxes represents an optimal action. So having boxes around all the numbers means that this is an optimal action for everyone. And because it's an optimal action for everyone, it would be stable, right? This is the best I can do given the situation. And it's also the best you can do given the situation. So neither of us would want to change because it's optimal for both of us to be here. So that's stable. So action 1, action C is the only pure strategy Nash equilibrium in this case, because as you see, none of the other cells representing the other situations have boxes around all the numbers. What this means is that when you need to find the Nash equilibrium, you can do this with drawing boxes around numbers. Follow the same method, which we will do again in a moment. Follow the same method of drawing boxes, considering every cases, and whichever cell or cells, there could be more than one, whichever cells have boxes around all the numbers would be a Nash equilibrium. We'll do this again in a moment. Something I want you to notice is that Nash equilibrium is not necessarily efficient. Take a look at the bottom right corner. This one. Notice that in this case, both players get 12. Yet in the Nash equilibrium, they only get 10. So the bottom right corner is actually better for both players. And we have a name for that. This is Pareto optimal. This is much better for both players. They both get more. Who doesn't like that? So Nash equilibrium is not necessarily efficient. It's stable, but a stable situation could mean everyone is poor. Think about it, right? It does make sense. What's happening here is that the Pareto optimal situation, where everyone is better off than the Nash equilibrium, is not stable. In the Pareto optimal, one of the two players have an incentive to switch to another action. So you can't maintain the Pareto optimal. Efficiency is not the same as stability. And in the real world, think about the situation. Let's say you're in a world where everyone is selfish, and we are in maybe an apocalyptic world where you have to fight for survival, right? What happens when let's say we all have some supplies that help us to survive? People might fight for the supplies, right? Oh, I see that you have. I see that you have supplies. If I get your supplies, I would be even better off. So I kill you and get your supplies, something like that, right? I rob you at least. So we'll fight, and when we fight, we get hurt. Maybe we both die. Then we reach a situation where it's stable because we both die, something like that. A situation where neither of us has any supplies, on the other hand, would be stable because you have nothing, I have nothing, there's nothing to fight over. So now, just now, we said that player 1 always wants to take action 1. So in any scenario, all scenario, that's called a dominant strategy, right? Or dominating strategy. An action that is always taken. And an action that is always taken, no matter what the opponent does, is called a dominant strategy. Action 2 is called a dominated strategy because it's never taken. It's never optimal. Right? So dominant strategy means that it's always optimal. in terms of finding one. That means you're looking for action that has circles or squares around all the corresponding payoff. Remember in our case just now, we have highlighted the number, the payoff corresponding to action 1 if player 2 picks action C. We have already also highlighted the payoff for action 1 corresponding to the situation when player 2 picked action D. So you have boxes around all the payoff of action 1. So that would be a dominant strategy. Boxes around all payoffs of that action. A dominated strategy would have no boxes around any of its number. That would be a dominated strategy. Okay? There's also this idea of strictly dominant strategy, which is a situation where it's strictly better off to take one action over another. So in this case, 10 is strictly bigger than 9, right? 10 is actually bigger than 9, and 16 is bigger than 2. So it's actually strictly better off to use action 1. You actually get higher payoff in all scenarios. And action 2, we call that strictly dominated. If I modify the game slightly, notice that I've increased the payoff of action 2 when player 2 takes action C to 10, right? Notice that in this case, action 1 and action 2 actually gives player 1 the same payoff no matter what he does, as long as player 2 is picking action C. In this situation, you're supposed to highlight both payoffs, right? And for the second one, 16 is still better than 12. So in this case, action 1 is strictly better off than action 2 in some cases, and at least as good in other cases. We call that weakly dominant strategy. It's arguably still better, right? Action 1 is still arguably better because it's at least as good as player 2. Action 1 is at least as good as action 2, and sometimes strictly better. So arguably, it's still better, and that's the one you should pick. So that's why it's still a dominant strategy, but it's only weakly because in some cases it's not better. It's just equal. And action 2 is called weakly dominated. Why do we introduce this concept of dominated strategy? Now, that's because the elimination of dominant strategy sometimes can help us eliminate unnecessarily actions in a game. Actions that would not be taken by players. So because the dominant strategy is never the best, we can remove all those actions. We can argue because it's never going to be used. So in our example, the original example, we can say, well, these actions are never taken, so we don't need to put them in the game to begin with. So we can eliminate them. In particular, in our case, we know that player 1 is not going to take action 2, so we don't need to put them in the game. Put it in the game. So let's eliminate it. But what happens when you do that? When you eliminate action 2 from the game's simplified, and it changes player 2's decision, right? Player 2 would choose action C if player 1 chooses action 1, and choose action D if player 1 chooses action 2. But since action 2 we just eliminated from the game, there's no reason for player 2 to choose action D anymore, because we know that player 1 never chooses action 1. So in turn, we can eliminate action D. Once you do that, the game actually simplifies to just a single scenario. Player 1 chooses action 1 and player 2 chooses action C. And that happens to be the Nash equilibrium. So that's another way we can move towards the Nash equilibrium. In more complicated games, this is quite helpful in making the game more manageable by making it smaller. It doesn't necessarily always lead to the Nash equilibrium directly, but it's helpful in reducing the complexity of the game. Okay, so this is a strategy you will see more often in a more complicated game when you take a course in game theory. So what we just did is that the elimination of one dominated strategy can lead to the elimination of another originally not dominated strategy. So this process is called the iterated elimination of dominated strategies. You keep removing things that they don't use. You keep removing things that they don't use. So in the end, you get a much simpler game. So that's something you should be able to do. All right. Now I want you to try it, to do it yourself. This is a game called Battle of the Sexes. The interpretation is David and Mary are trying to go to watch a movie together. David likes action movie, so he gets more utility. He gets a higher payoff if he goes to the action movie. Mary likes romance movie, so she gets a higher payoff if he goes to a romance movie. However, the most important part of all is that they go together, because this is supposed to be a date, so they cannot go alone, right? So they get nothing if they go alone. Now find the Nash equilibria in this game. Just to help you out, let me indicate once again what you need to do. Remember, you start with assuming that the other player is going to take a particular action, and you ask what the current player is going to do, given what the other player is doing. So you begin, you should ask which movie David would go if Mary has already chosen the action movie. Then you should ask what David would do if Mary has already chosen the romance movie. After you do that, you switch to I can't switch color for some reason. Right. After you do that, you switch to Mary. You ask what would Mary do if David has already chosen the action movie. And finally, you ask what Mary would do if David has already chosen the romance movie, right? And the box and the cell with the most boxes or circles around the numbers, well, the cell with circles or boxes around all the numbers would be a Nash equilibrium, right? Try that out and tell me how many there are. Okay. So I'm going to just switch once again. I'm going to follow what I did, so because it will make it easier later on. Just going to switch the colors. All right. So draw circles. Just draw circles. Remember, the number in front of the comma represents the payoff for David, and the numbers behind the comma represents the payoff of Mary. So for David, you should always be comparing the number on top versus the number at the bottom. Like 2 versus 0, which one will you choose? 0 versus 1, which one will you choose? For Mary, you should be comparing the number on the left to the right. 1 versus 0, which one would she choose? And 0 versus 2, which one would she choose? Okay, so some of you already figured out the answer. How many? 2, right? Yes, 2. There are 2 Nash equilibria in this situation. Let's try that out. Let's start with 1. Suppose Mary has chosen to go to the action movie. What would David do? David wants to, the most important objective is to go together. So David is looking at choosing the action movie and getting a payoff of 2 versus choosing the romance movie and getting a payoff of 0. So obviously 2 is better. It doesn't hurt that he actually likes action movie. What about if Mary has already chosen the romance movie? Well, once again, the objective is to go together. So as much as David likes action movie, if he goes along, he gets a payoff of 0. So he's going to choose the romance movie. What about Mary? What about Mary? If David has already chosen the action movie, by the same logic, Mary wants to go with David. So she's choosing between getting payoff of 1 versus 0, and she's going to choose payoff of 1 going to the action movie because the point is to go together. And finally, if David has chosen the romance movie, that would be so nice for Mary because she actually likes romance movie. So she's going to go to the romance movie. So the cells with circles around all its numbers are Nash equilibria. So you have 2. There's one here at the top left corner, and there's one at the bottom on the